Good. Now, the last thing about that is we already know how to map the reference element to the physical element and how we describe the geometry transformation, how to compute the Jacobian, how to compute all the geometry transformation coefficients. And we know how to generate them when it comes to the values. Now, the last thing is how to compute the integral. You're already laughing.
It's the worst part.
Why the worst? It's like a beautiful piece of theory. And the idea for that is that people have come up with Gauss integration or Gauss quadratures. The Gauss quadrature is defined in a very, very simple way. For the 1D case, it's said that you can integrate any function f at x over the integral from -1 to 1, and the Gauss quadratures are always defined on this interval. So if you want to use any other interval, well, again, please map to the other space. Can be exactly calculated as the sum of some Gauss weights times values of the original function at the Gauss integration points. Now my heart is bleeding because I really need to erase something more. Not that. So now, as a rule of thumb, okay, let's assume there are multiple Gauss quadratures that are defined. Let's write a couple of them. You can have Gauss quadrature with just one point. Then C1 is nothing else than 0. And can anyone guess what's the weight? It's not a difficult. Really?
It's from -1. It's half.
Really?
It's not half? No, it's 2.
It's 2. Why?
Because it simply resembles the rectangular.
Exactly. Like, imagine you would be integrating unity from -1 to 1. The result is 2. This one needs to give you the same. This would be 1 at x equals 0, well, but then the weight needs to be 2. If you've got Gauss quadrature with 2 points, it turns out that, well, psi 1 and 2 equals either plus or minus 1 divided by square root of 3, and each of the weights are symmetric. What are they?
Half and minus half.
No.
But we should again calculate them from the condition that calculating the integral of constant unity function is 1.
Which means that two weights that are symmetric
Plus and minus 1.
symmetric are both 1. Well, again, because taking unity at minus, if you want to integrate such a function from minus 1 to 1, and your integration points are somewhere here and somewhere here, as taking 1 and 1. So you need to, and this sum tells you, okay, let's take the first value, the first weight, times the value at this integration point, which is 1, plus, well, at the other, again, 1, times the weight, and the weight needs to be 1 then. If we define the Gauss quadrature with 3 points, it turns out that C1 and 3, they are symmetric, and they are plus and minus 3/5. Xi2 is, well, to some extent also symmetric. It's just at 0. Weight 1 and weight 3 equals 5/9, and weight 2 equals, you can calculate that, equals not minus. If you integrate unity, to what does it need to add? Because again, all the weights together, they need to sum up to 2. If you want to have more Gauss quadratures, Wikipedia will help you. But now let's review it. Let's review it, and hopefully I didn't erase too much. Now, what we do is see. Now, we are replacing this integral by the Gauss quadrature rule. So we, let's say sigma from k because it's already the third index in our formula, k from 1, let's say to 2, we can use this we would be using this Gaussian quadrature. So we need to calculate this d phi j d psi calculated at psi k times d phi I d psi calculated at psi k times d psi dx square calculated at psi k times Jacobian calculated at psi k times the kth weight. Finished. Okay? It looks more and more difficult, but to be honest, it's right now we are closer and closer, and it's like it's exactly what we want to have. It starts to be simple.
And we are still in the one dimension.
And we've implemented Navier-Stokes in 3D for convection, diffusion, in stationary terms, and everything else. And it works. Good. Just quick remarks. What's beautiful about Gauss integration formula? That they really require very, very few integration points. So these sums is not like, calculating the integral by dividing into small subdomains. You take just a few, and I will tell in a minute how many. You just take a few integration points to have either exact or quite accurate integral values. Now, one of the last things to be said about geometry transformation. This one, if you've got linear elements and you need to calculate it at psi k, does it change anything?
No, it's constant.
Exactly. If you've got linear finite elements and linear shape functions, then this one is constant. Then this one is constant. Well, but if you haven't got linear finite elements but quadratic elements, then obviously the gradient will change linearly. So you already need to calculate. So you already need to calculate that.
Yeah, but then it's like still constant for all reference.
No.
No? Okay.
No, it isn't. No, definitely it isn't. Even in 1D case, you may have such a
No, I mean like it's the same. Okay, so it's the same for all the elements. So like you compute it once and...
okay. Yeah, for all the elements because you got reference elements. Yeah, but it's different at each integration point. Now, what about the geometry transformation? Because this term comes from the geometry transformation. If you've got linear geometry transformation, then this matrix, if you use in 2D, this geometry transformation and calculating this matrix for whatever psi and eta gives you the same result. So the inverse of that is everywhere inside the element is exactly the same. So you can calculate it once for the whole element, and it's constant across the element. Then the Jacobian, I probably know what you want to ask. And the answer is yes.
Thank you.
If you calculate the Jacobian, then it's also constant for the whole element. If we are talking about 1D linear elements or triangular linear elements. Well, weight is nothing else, it's just some scalar value. Yeah.
What about nonlinear elements, like geometrically nonlinear elements?
Okay, in a minute. Just one final remark about geometry transformation. We didn't cover it yet, but well, I have said that these values are constant for 1D linear or triangular linear elements. That's true. If you want to define a quad element, what are the shape functions that we are using in this case? Well, writing any interpolation is done actually the following way, like some function psi eta is having, well, some constant coefficient plus b times psi plus c times eta plus d times xi times eta. Okay? That's how we define, and this, you can call it linear quad element, but to be honest, people very, very often call it bilinear. Bilinear, it doesn't have any squares of any of the variables, but it does have this bilinear term. Hmm?
Do we have in the software like ANSYS somewhere we can change the number of points
For the quadrature?
for the quadrature?
Yes, I think you can, especially in the structure ANSYS code for mechanical strength simulations. I think there is somewhere some tab where you can specify how many integration points the Gauss rules should use.
Yeah, it's I can confirm that it's true. You can change that, and also you can access the values of those integration points if you want.
Yeah.
But only in mechanical, because like Fluent is easy.
Where Fluent is find volumes.
So I think that the only ANSYS product is the mechanical that uses.
But now, if you're using bilinear elements, the quad elements, then see, calculating the Jacobi matrix, well, nothing, constant, constant, linearly dependent on one of the variables. So for the bilinear element, the Jacobi matrix is not constant anymore across the element. So when you're calculating the integrals, then you really need to evaluate, well, first of all, you need to evaluate, when it comes to geometry, you need to evaluate this one at the given integration point. Well, as you mentioned, there are not many integration points, and the good thing is that you have exactly the same integration points for each element because, and it's one of the nice features, nice properties, because you are working in the reference elements. So once you've computed that, no, sorry, it's geometry transformation. So the value of the geometry transformation will really depend on how your element is re-entered. So you need to calculate that for every element, but you will, but for example, these two, even if they depend on.
I think like later, if it's written like with the like matrices, then you can extract the nodes values, and the rest it's.
Well, you've got basically the choice in your code to either store these matrices at the integration points for each element. That's not, you know, like it's not crazy amount of data, so you can do it, but it's already something to be stored.
It depends how we want to optimize the code. So for performance
And it also depends on how often you assemble the matrix. Because maybe you've got the linear system, you just assemble the matrix once, and then you run the code. Good. So you had the question about nonlinear geometry. Okay, and before I answer that, any more questions to either Gauss quadratures or geometry transformation?
I just want to say this answered one of my problems that I had for 2 days, but because I thought that the 1D reference element would be also spanned from 0 to 1 like the triangle.
Okay.
And well,
It's not. It's not.
This explains a lot of my problems
Hmm?
with the code.
We could.
Yeah, we could, but the convention that is generally adopted in the world is from -1 to 1, and I think it's greatly associated to how the Gauss quadratures are defined.
In a similar way, the quadrature, the quads are defined
Yeah,
at
they are
-1,
also.
1, -1, 1,
Yeah.
not 0.
Yeah, exactly. If we are talking about the 2D elements, then the quad element, the reference one, is always defined this way, from -1 to 1, from -1 to 1. And the nice thing about Gauss integration formulas is that you can easily derive the two-dimensional Gauss integration rules, taking actually the Cartesian product of two one-dimensional Gauss quadratures. So we'll probably end up with some squares of the subsequent weights. Well, and the integration points are exactly the same, just either with respect to psi or eta. Also, and that's something that you need to look for, because for the triangular elements, I don't even remember. Like, there are many Gauss quadratures already defined on triangles, because basically you cannot use this to calculate anything on the triangle. They need to be properly derived, optimized, and calculated. And to be honest, it's not an easy task. Really, it's not an easy task for the triangle to calculate the Gaussian quadrature points. And I think I cannot draw it well, but there will be some more points, and you simply need to. I think until you've got not so many of them, I think you'd still find some. I think you'd still find some rules where they are located. But if you need to go to higher integration points, then there are absolutely no rules. And they need to be optimized usually by solving really very complex optimization problems. So if you need it for general shapes, look for good scientific papers where they are already calculated. Good. And the last question about Gaussian integration is how accurate it is. And what? The Gauss quadratures are derived in a way that they should, with infinite accuracy, integrate polynomials. Okay? Now, a good question, if you think a while, you should guess it. If you've got the Gauss integration formula with just two integration points, what degree, polynomials of up to which degree can it integrate accurately? 3. Why 3? Why 3? Because how many free parameters do you have in the Gaussian quadrature to optimize it in a way that it integrates, well, possibly many first polynomials accurately? Well, obviously you've got, for 2 points, you've got 2 integration points. Well, they happen to be symmetric, but it's just coincidence. So you've got 2 integration points that you can optimize, and you've got 2 weights, also happen to be symmetric by accident, but generally you've got 4 free parameters that you can optimize. And now, any polynomial is like a plus bx plus cx squared plus dx squared plus 4 and so on. You've got 4 free parameters, so you can write a system of equations to fulfill the value of the integral correctly for the polynomials of the third order. So basically, it said that polynomials of degree 2n plus 1, 2n minus 1, can be integrated with infinite accuracy by the Gauss quadrature. Okay, so it's really a very, very efficient way of carrying out integration in the numerical code. Even if you see that we run into bilinear elements, let's make a short analysis. If you're using bilinear elements and you want to compute the diffusion matrix, the local diffusion matrix, how many Gauss integration points do you need to have for a 2D element? This one, for the bilinear element. Is it constant? Is it linear? It's linear. This one, stupid question, same, linear. This one, good, square, linear. This one, linear. So which, and that one is obviously, sorry, this is the function. Yeah. So which order is it? Degree? 5th. How many? Exactly. 3 Gauss integration points in one dimension times 3 in the other one. If you use 9 points in a quad, you end up with analytically calculated values, although you've used numerical procedure.
But if we have some diffusivity as well, but if we have some diffusivity as well in the summation,
that is variable.
Yeah.
Yeah. But however, you can calculate. Okay, but let's assume you've got constant triangular element. What's the order? Constant, 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 constant. Diffusion matrix, 1 integration point, just 1. If you do the mass matrix, then it wouldn't be the gradient, it would be the function. So linear times linear, constant, constant. Well, second order or bilinear. Well, for the triangles, you can. It holds for the 1D case, so you can already not guess for the triangles how many integration points you need to have to integrate polynomials of 2nd degree on the triangle accurately. Just go to the lookup tables in the scientific papers, and you simply have the, boom, and integration points. These are the values. Integrates polynomials of up to 3rd order accurately. Okay, if you want to do curvilinear elements, so basically have a triangle like that. It's fully possible. The thing is, and the concept is simple. You start with the reference triangle.
And the reference one is like, yeah.
And the reference one is that. But if you want to have curvilinear elements, this means that you need to have higher order transformation of the geometry. So it cannot start with the linear elements, because a linear element will always also, transform the edges into lines, straight lines. So you need to have at least second order triangle, and then you will map these vertices to somewhere here, and each of them will be a second order function.
So the Jacobian will be not 2 by 2 by...
No. Jacobian will be still 2 by 2, because it always transforms psi eta into xy.
But it won't be constant. Yeah, it won't be constant, because you would have to, like, every point will be transferred in a different manner. So it won't be constant, it will be like function. Yeah, like 4 functions in fact. Yeah? I mean the Jacobi.
Well, simply this one will be supplemented with additional functions, and you will have terms like a constant, psi, eta, psi squared, psi eta. This is the basis to build the shape functions. So you will need to calculate the derivatives, but as you see, the derivatives will always be linear with whatever respect to your calculating the derivatives. So the Jacobi matrix will be linear. The inverse one also will depend linearly on space. Whereas to be accurate, you will need to use higher order Gaussian integration formula, but you don't always use, like I would say, full rank integration formula. Sometimes you use lower order Gaussian quadratures, and you agree to having lower accuracy, not having analytical solution. And sometimes it's done on purpose. I think it's in mechanical strength simulations, it's sometimes done, and it can improve the stability and the conditioning of the system. I think it's partly like introducing artificial diffusion to what we've covered in fine volumes. It's sub-integration, under-integration. I think it's got a special name.
So basically the only difference will be that the Jacobi matrix now will consist of linear functions in case of second order with respect to geometry element, and also that it would be nice for us to evaluate the Gauss quadratures on more points than 2.
And that's it.